what is getting transferred in a redox reaction? It's not protons. What's getting transferred? It's electrons. So we need a pair. Okay, we need a couple. Okay, a couple. So that's called a redox couple. I'm a giver, I get oxidized. Susanna is a taker of electrons, she gets reduced. Okay, so if you give away an electron, you become oxidized. If you take an electron, what happens? You become reduced. All right, you become reduced. So let's balance a redox reaction. Okay, not any type of reaction, but a redox reaction. Okay, so we're going to balance a redox reaction right now. So in our homework, or if you in our quiz, when you balance a redox reaction, which is a transfer of what again? Electrons. It's either going to be done in acid or base. Okay, acid or base. So if you're doing this in acid, you have a lot of two things. What are those two things you have? A lot of when you're acid means, what do we know when we have a lot of acid around? Did you say protons? Yes, protons is absolutely the right answer. And then we have water. Okay, everything is done in water. Okay? So with that premise, we will work on this equation here. Balance the following chemical reaction in acidic medium. So once again, when we say acid, you have protons and water. If it's base, what do you have a lot of? Water and what else? Very good. OH minus. Not OH, OH minus. And everything is in water here. All right, so we're going to split this reaction up. Okay, we will split the reaction up. You see here we have iron plus 2 going to iron plus 3. Okay, iron plus 2 going to iron plus 3. Okay. Here we're going to deconvolute. What does deconvolute mean? Just break it down. Okay, we're going to break this down into oxidation and reduction half reactions. We'll break it down into oxidation and reduction half reactions. Okay. So we have plus 2 going to plus 3 iron, Fe. So how many electrons? Remember, in a redox reaction, we are dealing with electrons and electrons only. Okay, how many electrons do I need to balance the charge? Okay, I'm already at balancing the iron, 1 iron and 1 iron. But how many electrons do I need to balance the charge? Okay, so here I got plus 2. Here I got plus 3. Okay? So remember, an electron is E minus. So how many electrons and where? How many electrons and where do I put it to balance the charge? Okay. I'll put the electrons, does everyone see this? I'll put the electrons, and first of all, how many? Okay, it's 1 electron, I'm going to put it here. Okay, does everyone see that? Okay, so what's my charge on the reactant side? Plus 2. What's the charge on the product side? What's plus 3 minus 1? 2. So plus 2 here, plus 2 here, we are balanced. 1 iron here, 1 iron here, we are balanced. All right, now question for you guys. Is this an oxidation reaction or a reduction reaction? We lose electrons in oxidation. We gain electrons in reduction. Okay? Lose electrons oxidation, gain electrons in reduction. So we lost 1 electron, so we are oxidation. Okay, this is an oxidation half reaction. Okay? If we were a battery, let's say we are a battery which consists of an anode and a cathode, what would this be? Would this be the anode part of the battery or the cathode part of the battery? Red cat eats an ox. Red cat eats an ox. So anode oxidation. Since this is an oxidation, if this were a battery, it would serve as the anode. All right, so that's 1 down, because for every oxidation there is a reduction. So we got to do the second half. Basically, we're splitting this up into oxidation and reduction. right, now we'll do the MnO4 minus. This is called permanganate ion, just so you know, permanganate. And it goes to Mn plus 2. Okay? Okay, we got one Mn here, one Mn there, but we have an oxygen. Okay, an oxygen. So we need to balance the oxygens. What do we balance the oxygens with? We're an acid, so what do we have a lot of in acid? Water and H2O, water and proton, and we'll balance it with water. Very good, Susanna. How many waters and in what side? Okay, does everyone see need 4 H2O? 4 H2O. Okay. All right, so that gives us 4 oxygens, 1 Mn, 1 Mn. Okay, now we got hydrogens. What can we balance the hydrogens with? We're an acid, so what do we have a lot of? We have a whole bunch of it in acid. H plus protons. So I'm going to balance this with 8 H plus on the other side. Okay, this is what you'll do in acid. Okay, if it's basic, you'll do the same thing, but you'll add OH minus. All right, and now finally we will balance the charge, okay, with electrons. So we have plus 8 minus 1 is 7. Plus 8 minus 1 is 7. Okay, plus 2 here. Okay, so we have a plus 7 here and a plus 2 here. So how many electrons and where should I put it? So you see here the electrons are in the product side. So where should the electrons be here? They should be on the reactant side because for every oxidation there's a reduction. But how many electrons? Is it 1? Is it 2? Is it 3? Okay. It's going to be 5. Right? No, hold on. I'm wrong. 8 minus 1. Yes, it's 5. Okay, 5 electrons. Okay. So minus 5 plus 8 is plus 3. 3 minus 1 is plus 2. And then we have a plus 2 on the product side. Okay, everyone see that? Okay. 8 minus 5 is 3. 3 minus 1 is 2. And plus 2. So is this oxidation or reduction? Okay. So we gained 5 electrons, so this is a reduction. Here we lost 1 electron, here we gained 5 electrons, so this is a reduction. And where does, in a battery, where does reduction happen? Okay, reduction, cathode, anode oxidation. Red cat eats an ox. This is in the cathode. So these are our 2 half reactions that come together to give you this reaction. So now we're ready to balance it. We'll cancel out the electrons. All right, so I'm going to multiply the top reaction by 5 because we can't have electrons floating around. Okay. I'm going to multiply the top half reaction by 5. So when we do that, okay, it's going to be 5Fe plus 2 goes to 5Fe plus 3 plus 5E minus. We'll do nothing to the bottom because we just leave it like that. So this is going to be, let's just do it here, 5E minus plus 8H plus MnO4 minus goes to Mn plus 2 plus 4H2O. Okay. And I think we are almost done here. This 5 and that 5 cancels. This is what you want. Okay, that's what you want. You don't want free electrons floating around. And then our final net redox reaction, combining oxidation, combining reduction, it's going to be this. Okay, 5Fe plus 2 plus 8H plus plus MnO4 minus. And this is going to go to Mn plus 2 plus 5Fe plus 3 plus 4H2O. Okay. And I think that's the right answer. Let's double check. We can always double check our answer. All right, so here we have 5Fe, 5Fe. 8H plus 8H, sorry, 8H is 8 H's. Okay, we have 1 Mn, 1 Mn. How many oxygens? 4 oxygens, 4 oxygens. And now we'll balance the charges. Okay, how will we balance the charge? Okay, 5 times 2 is what number? 10 plus 8 minus 1. And then here we have 2 plus 15, 5 plus 3. Oops. 5 times 2 is 10 plus 8 minus 1. On the reactant side gives us 17. 2 plus 15, 5 times 3 on the product side gives us 17. This is balanced. So this is how you balance an oxidation reduction reaction. Split it up into its anode and cathode, split it up into its oxidation and reduction components. Okay? And if it's in base, you just do add OH minus and water. All right, so I'm going to switch gears now, and I'm going to teach you how to read this. Okay, so you can bring this to the exam. Okay, bring this to the exam. Do you have copies of this? I think I gave out copies on Friday. If not, I can give it to you after class. Okay, so you want this for the test. Okay? All right, bring this to the exam and let me explain this to you. All right, how do we read this? First and foremost. All right, one thing first and foremost is that these are reduction reactions. Okay, you see the word here? Reduction. I also see the word here, standard. Okay, so standard reduction potential. All right, so all of these reactions are reduction reactions. So are they gaining electrons or losing electrons? Reduction. Gaining, okay? So this one is gaining 2 electrons. This one is gaining 2. Okay, this one is gaining 1. This one is gaining another 2. This one is gaining 1. Okay, we have another one here that's gaining 5. Okay? So all of these are reduction half reactions. Okay? So that's point number 1. All of these are reduction half reactions. So, and they have a voltage or a potential. This is a potential or a voltage associated with this. Since all of these are reduction reactions, we can also call it E cathode, standard state. Okay, standard state. So another way of saying this is E cathode. Okay, what does this little O mean? It's called E naught. But what does that naught mean? Yes, very good. It means standard state. Okay. All right, so that's point number 1. All of these are reduction half reactions. Okay, so all of these are E cathode. That's point number 1. Okay. Point number 2, a positive 2.87 volts. Okay, do you think that would favor the products or reactants? A positive voltage. What would it favor? Let's go all the way down. Minus 3.05 volts. Okay, what do you think that would favor? Products or reactants? Okay, what do we know about negative voltage? It's what did you say?
I said it's dead.
Dead. Okay, so it ain't happening. Right, very good. So a negative voltage is not favoring the products. Okay, we don't buy negative voltages. Okay, so this is favoring the reactants. Would this reaction like to happen? Susanna, lithium plus E minus goes to lithium. Would that like to happen if it gives you minus 3.05 volts? No. Okay, no. So this half reaction favors the reactants. Okay, this is just simple common sense. Okay. What about this reaction here? F2 gas plus 2E minus goes to 2F minus, gaining 2 electrons, positive 2.87 volts. What do you think this would favor? This half reaction, products or reactants? This would definitely favor products because it's eliciting or giving us positive 2.87 volts. Okay, so positive voltage is a good thing, right? Because that favors the movement forward. Positive voltage will favor the movement forward. Okay, so that's point number 2. If you are positive, you're favoring the product side. Okay, but remember, this is a cathode. What are the two things that make up a battery? Cathode and yes. So when you add the cathode and anode, they have to be positive voltages. This just means this half reaction is favored. This half reaction is favored. But really, it's the cathode and anode together that need to be positive, right? The cathode and anode together that need to be positive. So that is positive voltage favors the products. So number 3 here, okay, I'm going to take this reaction, which is E cathode, I'm going to flip it. Okay, I'm going to flip it. So let's call this reaction 1. Half reaction 1, because these are half reactions. Okay, we're going to flip half reaction 1. When we flip half reaction 1, this is what we get. Okay, flipping the reaction, we're going to get when we flip the half reaction, we're going to get 2F minus goes to F2 plus 2E minus. Okay, so I just flipped it. Okay, so when I flip it, what does this become? Does it still E cathode? This time I lost 2 electrons. Okay, so is it the cathode still? Yeah, this is the cathode. Okay, what will this become? This will become the anode. Very good. Okay. And I flip it. Is this still going to be positive 2.87 volts? Okay, what will it be? Negative? That's the good guess, and it's the right guess. It will be negative 8.7 volts. Okay, negative. Okay. So rule 3, or point number 3 here is if you flip a reaction, you flip the sign of the voltage, the cathode becomes the anode, or the anode becomes the cathode. Okay. This is oxidation. It lost 2 electrons. All of these in this table are reductions because they're gaining electrons. Okay, so flip the reaction. You flip from anode to cathode to anode, and you flip the sign of the voltage. In this specific reaction, the cathode becomes the anode. so this next important point is very, very critical. So I want everyone's attention here for this one, okay? More so than before, okay? So I'm going to take this reaction here. I'm going to take this reaction. I'm going to multiply it by a number, okay? Let's say, give me a number, Susanna.
2.
I'm going to multiply this half reaction by 2. Okay? So when I multiply this half reaction by 2, I get 4F minus goes to 2F2 gas plus 4E minus. Okay? This is still the anode. All I did was multiply it by a number, 2. This is still the anode, but what is its voltage? Okay. It's still going to be minus 2.87 volts. Okay. In other words, all of these voltages never change. They are invariant. Okay, you never want to change this number. You do not divide this by 2. You do not multiply this by 2. You do not, let's say Susanna said 4. Okay, you do not multiply this by 4. You do not divide by 4. So all of these numbers will never change. Okay, so please remember that. Okay, all of these numbers will never change. All of these numbers will never change. Okay, in other words, they are invariant. I'll say all of these voltages will never change. In other words, we call that invariant, meaning that you cannot multiply them by 2, you cannot divide by 2, you cannot do anything with them. Okay, they just are there. All right, now the next thing is also kind of difficult, but let me see if I can explain this decently. Okay. All right, so I want you, Susanna, again, to pick any reaction. Actually, I'll do this for you. Okay. You see this half reaction? Okay, I'll highlight it in yellow. Cl2 plus 2E minus goes to 2Cl minus, and this is, what is the voltage? Oh God. Plus 1.50 volts. Is it 1.36 or 1.50? Okay, this is 1.36. All right, so I just picked one, or I forced you to pick one, okay? Okay. So we're going to pick one, all right? Any one you pick, the one below it can get flipped and give you a positive voltage. Pick one, any one. The one below it can get oxidized. And when I say oxidized, it can get flipped. So pick one, any one, it can get flipped and give you a positive voltage, okay? So what that means is this Cl2 gas can oxidize 2H2O into O2 gas plus 4H plus 4E minus. Okay, this is called the diagonal rule. Okay, this Cl2 can oxidize, which means flip, Br minus into Br2 liquid. Okay, it can flip it. This will give you a positive voltage. Okay, what do I mean by that? Let's write this down here. Okay, we'll write this down. So pick one, any one. Whatever the one you choose, anything below it can get oxidized. Anything below it can get flipped. So I'm going to write the one that Susanna chose. Okay, you pick any one of these. Go ahead.
FE3.
Yeah, we'll do this one.
Oh, that one.
Yeah, or that I chose. Okay. All right, what is the voltage here? Plus 1.36 volts. And what did we say this was, anode or cathode? These are cathodes. Okay, let's pick one below it, any one below it. Okay, we'll pick this one below it. We'll highlight it in pink. Okay, I said it can flip it. Okay, so let's flip this into 2Br minus. Goes to Br2 liquid plus 2E minus. Goes to Br2 liquid plus 2E minus. I flipped it, so if I flip it, what does it become? It becomes the anode. Remember, if you flip all of these, the cathode becomes the anode. And what is its voltage? Not positive 1.07, but what number? Negative 1.07. Okay, in this specific example, the two E minuses cancel. E cathode plus E anode is E cell. E cell, electrochemical cell. And this is equal to, what's 1.36 minus 1.07? It will be 0.39 volts, 0.29 volts. Positive 0.29 volts. Okay. And then our net reaction is Cl2 gas plus 2Br minus goes to Br2 liquid plus 2Cl minus. Okay, so this is our E cell. Is it positive or negative? It's positive. Okay, will that be a battery? No matter how weak it is, it's still a battery. So what can we say? We can say Cl2 has the potential, has the ability to take Br minus and oxidize it to Br2 liquid. So anything below it can get flipped to give you a positive voltage. Anything below it can get flipped to give you a positive voltage. Okay, does everyone understand that? Anything below it can get flipped. Whatever you choose, anything below it can give you a positive voltage when you flip it. What about everything above it? Okay, can Cl2 oxidize Au, this is gold, Au solid to Au plus 3? Okay, can it do that? Okay, the answer is no. It cannot. It will give you a negative voltage. Okay, Cl2 cannot oxidize, that means flip, cannot oxidize water into H2O2 and H+. It cannot. It will give you a negative voltage. So anything above it, it cannot flip. Then how do you get a positive voltage? You flip the one you choose and keep the one above the same. Okay? So anything above it, you flip the one you chose and keep the one the same. You keep it reduced, but you oxidize the one you chose. What if it's below the one you choose? Flip it. Flip it. These are the only two scenarios that will render you and give you a positive voltage. Okay, does this make sense? Okay, this is called the diagonal rule. Okay, the diagonal rule. Okay, let's do another example here. Okay. Cr is chromium. Okay, Cr plus 3E minus goes to Cr solid. Okay, so question for you guys. Can Cr plus 3 oxidize aluminum to Al plus 3? Yes. Okay, yes. Okay, yes. Okay. Or you can say, another way of saying it is that Al plus 3 gets oxidized, or I'm sorry, Al gets oxidized to Al plus 3, Cr plus 3 gets reduced to Cr. Okay. Or you can say Cr plus 3 gets reduced to Cr, Al solid gets oxidized to Al plus 3. Okay, whatever it is, the one below it can get oxidized. Now, can Cr plus 3 take nickel and oxidize it to nickel plus 2? Yes or no? It will give you a negative voltage. You cannot do that. Okay? It will give you a negative voltage. So how do I get a positive voltage? How will I get a positive voltage between Cr and nickel? How will I do that? What do I flip?
The one above. The current one. You're starting with.
So how do I get a positive voltage between these two? I flip the bottom one and keep the one above the same. How do I get a positive voltage between these two? How do I get a positive voltage between these two?
Subtract the voltage.
Okay, what do I subtract? What do I flip?
You flip the second bottom one.
The Al plus 3, the bottom one. Okay? Do you guys get this? This is confusing unless you think about it. Okay, this is also known as the activity series. The activity. See, if I give an electron, okay, now instead of Susanna taking an electron, because we are a redox couple, we have Royce, he's competing. So who gets the electron better? Who is good at taking the electrons? Who has better activity in getting reduced? Okay, so he's better at taking the electron, he's better at getting reduced than Susanna. So he has a higher activity. Okay, all of these are just activities. Who's better at taking electrons? Okay, this is the best in taking electrons. Okay, which is the worst? This is the best at taking electrons. Okay, which is the worst at taking electrons?
Last one.
The last one, very good. Okay. All right, shall we do one more? AgCl goes to Ag solid and Cl minus. Okay. So what can it oxidize to give you a positive voltage? Anything below it, okay? Such as it can take copper plus, flip it, convert it to copper plus 2, losing those electrons, it gets oxidized. So it can oxidize copper plus 2 to copper. It can oxidize copper plus 1 to copper plus 2, okay? What about anything above it? What do I have to do to get anything above it? Sam, what do I need to do? I chose this one.
Get something higher.
How will you get something higher? You flip that and keep the one above the same. Okay, so anything below it gets flipped, anything above it, what happens? You got to flip the original. Yes, you got to flip the original. These are the only two ways you get a positive voltage. Okay, so this is how you read the standard reduction table. So on an exam, question is, can H plus oxidize CD to CD plus 2? What would your answer be? Yes. Okay, can H plus oxidize CD to CD plus 2? The answer is yes. Okay. Can CD solid reduce H plus to H2?
Yes.
Yes. Okay. Can reduce. It can reduce. Okay, oxidize everything below it. Anything above it stays reduced. Okay. This is how we do this. Okay. All right, let's do one more here. Can barium oxidize, meaning lose electrons, flipping everything on this sheet. Can barium oxidize potassium to potassium plus?
Yes.
Okay, can barium oxidize, that means everything on this sheet gets flipped. Can it oxidize magnesium to magnesium plus 2? It can only reduce it. It cannot oxidize it. Very good. Okay. So this is how you read the table. Okay. All right. Finally, you see here this top one. Let's go all the way to the top. This top one gains 2 electrons to become F minus, positive 2.87 volts. Okay, so this is getting reduced. So we say it is a very good oxidizing agent. It is very good at oxidizing. In fact, it can oxidize everything below it, which means basically everything below this, everything in this sheet. So we say this is a good oxidizing agent. Okay, why is that? Okay, let's look at our example between the couple, myself and Susanna. Okay, I give my electron, okay, all the way to the first one. I give my electron to Susanna, okay? I get oxidized, she gets reduced. She is very good at oxidizing me. She is the oxidizing agent. Why? Because she's the agent that causes my oxidation. All right, let's go. So this is the best oxidizing agent. Okay. What is the best reducing agent? The bottom one. Okay. We call this reducing agent the best.
This ultimately has to do with their behavior, their electronegativity. Like if I'm looking at the periodic table, chlorine is the highest because it's the most electronegative.
Yes, you can think of it that way. Mm-hmm. Yeah. But some of these, like metals, we don't consider them as being electronegative because of their d electrons and d orbitals. So it's a right way of thinking, Sam, for fluorine and maybe some of the halogens in the group 1 and group 2A. But these metals, maybe not the transition metals, particularly zinc and chromium and cadmium and lead sulfate, and we don't think of them as electronegative. Okay, we don't consider lead sulfate or cobalt or nickel as electronegative. But you're right, this is very electronegative, this is very electropositive. So this is the best reducing agent. Okay, what does that mean? Coming back to the example, okay. I give an electron, I become oxidized, she takes it. She becomes the oxidizing agent because she causes my oxidation. Okay, what do I do to Susanna? I reduce her. I am a reducing agent. Why? Because I caused her reduction. I caused her reduction. I am a reducing agent. She caused my oxidation. She is a oxidizing agent. Okay? So it's kind of, I don't know, backward, I think. But Susanna gets reduced. She gains an electron. She gets reduced. She is the agent that causes my oxidation. I lose an electron. I become oxidized. She takes it. I am the agent that causes her reduction. You see this? Okay. So it's kind of like a backward definition, but I didn't come up with this terminology. All right. Bring this to the exam. I'll have copies available during test date as well. Okay. All right, let's look at some more of this thing here. I want to tell you about a notation here. What we have is an anode couple, a salt bridge, and a cathode couple. The salt bridge is 2 lines. Okay, a salt bridge is 2 lines. This is the abbreviation for a salt bridge. Okay, so what is a salt bridge and what is all this stuff here? Okay, so let's take a zinc solid. Okay, and we bathe it. We bathe it in zinc sulfate. Okay, dissolved in water. Okay, and then we have on a separate beaker, we have copper solid, a copper strip, and a copper sulfate solution. This salt bridge sort of keeps the ions equilibrated. You don't want to build up too many positive charges, too many negative charges. So that makes the ions so that they're equal. Okay, so there's not too much buildup of positive or negative charge. Okay, so that's what a salt bridge is. Okay, and it's generally abbreviated by 2 lines. Okay. So let's look at this reaction happening in this beaker. Okay, so if you notice here, I see 2 electrons coming out. They're coming out of this wire and going to this thing that measures voltages. Okay, so we have 2 electrons coming out. So zinc solid, okay, 2 electrons are coming out. So that's going to give you zinc plus 2 plus 2e minus. Okay. 2 electrons are coming out. Okay. Okay, what's the voltage associated with that? Okay. It's 2 electrons coming out, so it's not negative 0.76. It's going to be positive 0.76. Positive. Okay. Look at the diagram. 2 electrons are coming out of the zinc. And then they're going into the copper. So 2 electrons are coming out of the zinc. They're going into the copper. So 2 electrons are being lost from the zinc. This is an anode. And what we see here is the cathode. So it's not negative 0.76, but positive 0.76 voltages. I'm going to call this E anode. Okay, who takes those 2 electrons? Copper takes those 2 electrons, okay? So we have copper solid taking 2 electrons. Let's see here. Here we go. Copper solid taking those 2 electrons. And that is positive 0.34 volts, positive. Okay. Copper plus 2 electrons. Okay, is this the anode or cathode? This is the cathode, and what voltage do you guys see here? Copper solid 0.34 volts. This is the cathode. Okay, how many electrons are being transferred? Okay, this is a 2 electron transfer reaction. This is a 2 electron transfer reaction. So our net reaction is going to be zinc solid plus copper plus 2 solid. I'm sorry, copper plus 2 aqueous. I'm sorry, this is aqueous. Copper plus 2 is aqueous. Any ion is aqueous. Goes to zinc plus 2 aqueous plus copper solid. Okay, we add them together. We get E cell. And E cell here is 1.10 volts positive. Okay, so is this reaction favoring the products? Yes. Okay, you see this is something that happens spontaneously. Okay, this flow just happens spontaneously. And it's going to give you 1.10 voltages of potential. All right, so this is the net reaction. Okay, we're going to do this notation. So on the exam, I want you to go from here to here, from here to here. So what is the anode couple? Okay, it's going to be zinc solid, one line down, zinc plus 2. Aqueous. Okay, so what is the abbreviation for salt bridge? 2 lines going down. And what is the cathode couple? Cu plus 2 aqueous, one line, copper solid. Okay. All right. So what I want to tell you, hopefully convince you, is that these two, if I give you this on the exam, you should give that out. If I give that on the exam, you should go to this. Okay? So these are one and the same. You'd be able to go back and forth between this and this. This is called the galvanic cell notation. Galvanic cell notation. Okay, once again, the anode couple, this gets oxidized. Salt bridge, which is 2 lines, or joins the 2 beakers together. Keeps the ions from not building up in one beaker over the other. And then the cathode couple, the thing that gets reduced. Okay, so page 3, I'm going to go over this kind of fast. This is the way I'm teaching it to you. For those of you that are using the OpenStax textbook, they have a slightly different way to look at it. So this is the textbook version. If you're not understanding how I do it, you can use the textbook or OpenStax explanation. Here, the textbook doesn't flip it. Here, I'm telling you to flip it. Here, I'm telling you to pick one, and anything below it gets flipped to give you a positive voltage. If you want an alternative definition, check out your textbook. Positive voltage means spontaneous. Positive voltage means it favors the products. When we add cathode and anode. And then this is just a review here on page 4. If you multiply a half reaction by 0.53, it still is 0.53. Okay? The only thing that can change is the sign. How do you change the sign? You flip it. Okay? So the only thing that changes is the sign. And you change the sign by flipping the reaction. Okay? So these are invariant. Okay? The only thing that changes is the sign. Okay? The only thing that changes is the sign of the voltage. And then this one here is kind of the same thing, the diagonal rule. Again, pick one, anything below it gets flipped. the one you choose, flip that, keep the one above the same. These are the only two ways you can get a battery. Okay? So I am out of time. Friday is a holiday, I believe. So I'm going to give you a video as an extra credit opportunity. Also, I'm going to be very strict on the deadlines. Okay, don't turn it in unless it's by the deadline. So I'll give you some time. Turn it in at the right time, and I'll give you some extra credit points. And we will finish up this chapter today and early next week and start our review.